So the question that Rutherford's model didn't answer, however, was if you have these negatively charged particles orbiting around a positive charge in the middle, what's stopping the electrons from slowly going closer and closer and closer and just spiraling and hitting the nucleus? I mean, it makes sense, right? What do you think, Ian?
It's the positive charge would repel the electrons away.
No, wouldn't positives and negatives attract? So that's the big question. People realized that at the time, so they said, why wouldn't the electrons just go right in the middle?
Is it because of like one electron getting closer?
That's a good point. Like you're talking about, like this one would shield that one.
Yeah.
Not quite. People didn't really have an answer until Niels Bohr.
Are on their own axis.
That's exactly it. Niels Bohr was a Danish scientist from Denmark, and he said that electrons can only be stable at certain distances from the nucleus, or as Mike just put it, they're each on their own axis, or axes, or orbital.
Or axi.
So this was the Bohr model of the atom that was created. You have your positively charged nucleus in the middle, and you have electrons existing on these orbitals. Now they can exist on this first step, or on this second step, or on this third step. And in fact, they can jump up or jump down, but they can never exist in between them. And in fact, it's really interesting. Electrons have mass, so they are physical particles. This electron can physically move from this one to this one, but at no time is it ever in between. It literally teleports. It's a strange function of waves and particles. Electrons are very tricky.
What explains that? I bet it's not so.
You would need, well,
So why can't we all just be atoms and teleport?
we are atoms and we are teleporting. That's how I'm able to see you. Your atoms are jumping up and jumping down. That's why you depict an image onto my eyes.
This is.
We'll get to this in a little more detail later.
Wait, is that what we draw?
Yes. So let's make sure we're clear on the gaps here. So in 1913, Niels Bohr proposed a theory that electrons can only be stable at certain what? Distances from the nucleus. So that's your gap there. The electrons in orbit farther from the nucleus have more energy. So what we see in this model here are three different elements. The one farthest away has the most energy. The one closest has the least energy. Please sketch this Bohr model that you see here. Now this is definitely not to scale. First of all, that nucleus would be so small that even one little pixel on that screen would be too large. The electrons would be even probably 2,000 times smaller than that. So this is certainly not to scale.
And so we know they exist because.
I'll actually get to that. Yep.
Do they know, like, compared to each other, is the nucleus bigger than the electron?
Yes, we do know that. The nucleus is what we now know as a collection of protons. They didn't know that at the time. They just knew that the nucleus was this positively charged central area. What we now know is that the proton is about 2,000 times larger than the electron. And the electrons are just smaller than you could ever fathom anything being. The next step in the atomic model, these two scientists, we have Schrodinger and Heisenberg. If you're a Breaking Bad fan, that's where Heisenberg came from.
Schrodinger's cat, right?
Yep, this
Cat in the box.
cat in the box. Schrodinger was Austrian, Heisenberg was German. Oh, by the way, I forgot, I usually tell this story with Niels Bohr. Bohr was Danish, he was from Denmark, he was working in the 1920s, 30s, and 40s. What was happening in Europe at the time?
World War II.
Right, World War II was in the 40s. Before that was kind of Hitler took power in the early 30s and he started annexing country after country. Now, at the time, chemistry was really just kind of blooming and people were winning Nobel Prizes for these discoveries. When you win a Nobel Prize, you get a cash reward, which generally you donate back to your lab. And you also get a solid gold medal. Two German Nobel laureates, Nobel Prize winners, one of them was of Jewish descent, sent their gold medals to Niels Bohr in Denmark for safekeeping, because they thought, we're in Germany, the Nazis don't really like what we're doing, they might steal our gold medals and, melt them down for the war effort. So they sent theirs to Niels Bohr. Now Niels Bohr also had one of his own, he won. So he had 3 solid gold Nobel Prizes. Well, Germany annexed Denmark, and the Nazis basically knew that Niels Bohr had these 3 metals, and they were going to basically take the metals and use the gold. So he had to think of some way to hide them that would basically outsmart, any commander general that came by. And he knew that he couldn't just like bury them or like hide them in, a box or anything. So he thought he could use chemistry and actually dissolve the gold, creating gold ions, and then after the war, turn it back into basically precipitate it out. Now, if you guys remember that activity series chart,
Yeah.
gold was at the very bottom, which is why you can like throw gold in any kind of acid and nothing happens. In fact, that's how they clean gold. You drop it in acid, anything else dissolves away and the gold is left intact. So normal acid wouldn't work, but there is one substance that does dissolve gold. It's called aqua regia, which stands for or means royal water. It's a mixture of nitric acid and hydrochloric acid, and it does dissolve gold. So no. It dissolves the one thing that can't be dissolved by anything else. So yes, you would certainly die. So he dissolved the 3 gold metals in this glass of aqua regia. It changed it from like yellow color to red color. He set it on his shelf. The Nazis came, searched everything for the gold, and couldn't find it. After the war, he basically precipitated the gold back out of the aqua regia. He sent it off to Stockholm, Sweden, where they craft the metals and they reform them. So he basically saved 3 gold medals through chemistry.
Did the other 2 live? The other 2 guys?
I'm sure they got them back. I think they worked out. Yep.
This is kind of off topic, but what are Tums made from?
Tums is basically calcium carbonate.
And that, what is it?
Well,
Antacid?
a lot of what they have, right, it's Tums with basically a little bit of base in them. Now, what happens when you mix an acid and a base?
Nothing.
Salt water. So if your stomach has a lot of acid reflux, it's producing more acid than it needs, you take Tums, which is basically chalk with a little bit of base mixed into it. The base neutralizes the acid, basically produces salt, which gets dissolved into your bloodstream, and you urinate it out, and it creates water. So that's how you fight acid.
So it is chalk.
It's chalk based, but they basically take chalk and they add flavor and they add more base to it. All right, back to our study here. It was a good question. I like those. What Schrodinger and Heisenberg came up with was this idea of the electron cloud. Now, in the Bohr model, the electrons orbited in these like perfect little spherical or circular orbits. Well, what we later realized through all these mathematical calculations is that's not true. We know certain regions where the electrons exist, but they're moving so fast that we can never really pinpoint exactly where they are. But the way you draw the electron cloud is basically draw your nucleus in the middle, tiny positively charged center, and you just sort of shade around it. And you want to try to show that they're more likely to be found close to the nucleus, less likely to be found far away. And the way I like to demonstrate the electron cloud model is with a fan. So, in this fan, let's say each blade represents an electron. So how many blades here?
5.
So which atom has 5 electrons?
One of them.
Boron.
Boron. So let's say this represents a boron atom. Right now, if we took like a still image of this, you could tell there's 5 electrons and you can see exactly where they are. Well, if I were then turn it on,
They'll just blend into one. If you can turn it on.
I think I just broke it.
If you can turn it on. Can we use chemistry to turn it on?
There we go.
You dissolve it.
So right now, how many blades are on this fan? We still know there's 5. The number didn't change, but can you tell me exactly where they are? No, you can never tell me where exactly they are, but you know they're somewhere in this range. So that's what I mean by the electron cloud. We know there's a certain number of electrons, we know where they tend to be found, but you can never really tell me exactly where they are. Exactly. No. Okay, so sketch your electron cloud, please. I would just do a positively charged nucleus and then just sort of shade around it as best you can. Okay, guys, the next step in our model of the atom, and this is the last one that I'm going to talk about. There are hundreds of other steps, and there's hundreds of other scientists from all over the world that I could have referenced, but I sort of chose the most important 6. James Chadwick, British scientist, in 1932, he discovered the neutron. So now we know that the nucleus is not just this kind of positively charged area. There's actually neutrons in there. We know that they are about the same size as protons. That's your next gap. I should say neutrons are found in the nucleus. They're about the same size as protons. And they have what charge? Neutral, or you can say 0 charge or no charge. Okay, what I have next is basically summing up what we now know about electrons, or about atoms. And this is, most of this is review. Atoms are made up of protons, neutrons, electrons. Protons have a positive charge. Neutrons have no charge. Electrons are negative. Protons and neutrons make up the nucleus in the center of the atom. Again, nothing new. I'm sure most of you learned this before. Let's look at the final 3 bullet points. Try to say what they are before we even look. Electrons have a what charge?
Negative.
Negative charge, and they orbit the nucleus. The nucleus contains nearly all of the atom's what?
Mass.
Mass is what I'm looking for. It contains nearly all the atom's mass. I mean, neutrons technically does work there, but I'm looking for mass. And protons and neutrons both have around, the number there is 2,000. Actually, I think I gave a more precise number as 1,800. Yep. 1,800 times more mass than the electrons. And finally, electrons are located in the electron cloud, an area that surrounds and is much larger than the nucleus. You look up there, you see that little picture? That's definitely not to scale. If that were to scale, like if that nucleus were to scale, the electron cloud would probably be definitely outside the building, possibly like half a mile away. Well, that is a small atom. That's probably a helium, probably about the size of the building. All right. So that concludes what I have for notes. So the rest of you guys are going to have to take down. So please take out your notes, please.
I should do more of these fill in the blanks.
Yeah, I
And they're challenged.
like the challenge.
Better than taking notes.
Yep.
Take notes on Schindler's List.
I did that AP year too.
AP Euro.
Oh, I forgot. It's select world lit. God.
Okay, now a lot of this information is review from bio or physical science.
No, do we take notes on this in our journal?
Yes.
So first of all, what is atomic number? Who can tell me? Quinn? Yep, and what does that represent? The number of what?
Atoms?
Nope.
No. The number of atoms.
The number of protons. Number of protons in an atom is called its atomic number. And what I have up here is to identify which element an atom is, we look at the number of protons. Number of protons is what we use to actually identify which element you're talking about. So for example, the true definition of a carbon atom, you wouldn't say it's an atom that is a metal, it has a black color, it's a high melting point with 4 valence electrons. Those are all properties. The true definition of a carbon atom is any atom with 4 protons. Six protons. Okay, and just a few more examples. Every atom with 2 protons is a what?
Helium.
Helium. Every atom with 6 protons.
Carbon.
Carbon. Question?
Is this probably going to be an end?
Yes. Carbon, 8 protons is. Right. So So basically the point I'm making at this is atomic number equals number of protons, and that's what we use to actually identify what atom you're looking at. Which element, I should say.
So uranium has 92.
What was 6?
92. 6 is carbon. You just look up there. Elements are organized on the periodic table by their atomic number. That's kind of a more recent way of organizing it. Well, at least recent meaning like 1900s. When they first created the periodic table, they were organized by their atomic masses. And you may notice there are a couple points where the mass actually drops a little bit. So we've kind of adjusted that. We're going to go on to mass number. So the atomic number is the number of protons. Anyone happen to know what mass number is? It's not the same as atomic mass.
Number of electrons?
Nope.
The addition of protons.
It is the number of protons plus neutrons. Mass number, the sum of the number of protons and neutrons in an atom. Or just P plus N. So for example, a fluorine atom with 9 protons and 10 neutrons has a mass number of 19. I think I gave more examples, which we don't really need. 11 protons and 12 neutrons, 23. 1 proton and 0 neutrons, 1. That's got to be your hydrogen atom. So it's just protons plus neutrons. And again, this is all sort of more basic logic. If we know the mass number and the atomic number, we can find the number of neutrons. So for example, a carbon atom with a mass number of 14 has how many neutrons?
Oh.
No?
8.
8. How'd you get 8?
Minus 6. 14 minus 6.
Right, so what you need to do is look up the atomic number for carbon at 6. So carbon must have 6 protons. If the mass number is 14, 8. So it's just very simple math. Okay? Leads us to isotopes. What does isotope mean? Okay, let's go into it. So first of all, not all atoms of an element have the same number of neutrons. Atoms of the same element that have different numbers of neutrons are called isotopes. So not every carbon has 6 protons, 6 neutrons. Some carbons have 6 protons, 8 neutrons. Those are called isotopes. To identify isotopes, we write the element, and there's a typo here. Symbol. You write the symbol, then a dash, and then the mass number. You can also write the name out. Generally, we write the symbol. And I'll just go through some examples to make it clear. Another few seconds.
Yeah. It's in the regular.
Okay, so for example, oxygen with 8 protons and 8 neutrons,
What do you write the element symbol?
then a dash, and then the mass number. So for that top one, I would write O dash what? The mass number of that top one is what?
8.
Then the
No, that's the atomic number.
0.
16.
Oh.
Mass number, protons plus neutrons. So for that top one, you would write O dash 16. What would you write for the second one?
O dash 8.
O dash 18.
O
Good.
dash 3. O dash 4.
Well, not O. That next would be helium, so HE.
He's gonna start talking so we can focus.
Helium 3, helium 4. The bottom two, that's uranium. U-235, which is the dangerous one. U-238, which is the not so dangerous one.
I mess with you.
Because if you spin U-238, it's more than U-235, so you spin it out, weighs less. So U-238.
There's one more thing I want to mention that you guys should take down.
Yeah.
Another way we represent isotopes is called nuclear notation. You basically take the symbol, such as carbon, and in the upper left corner, you write the mass number. Carbon 14, carbon 12, just like that. So it's the mass number, not the atomic number.
Wait, so the mass number is the protons plus the neutrons?
Right. Those of you that took physical science, you may have learned about the different oxygen isotopes. That helps us know what the weather was like hundreds of millions of years ago. So the two common oxygen isotopes are O16 and O18. And by the way, looking at the atomic mass, which of these two do you think is more common?
O16.
Right. We'll get to atomic mass in just a minute. So this is how you write with nuclear notation. So the two types of uranium, U-235, U-238. So you put the mass number, not the atomic number. I mean, the atomic number you should know, or at least like be able to look up.
Mutation is just the mass number.
Just the mass number in the upper left corner. All right. What I have next, it's just kind of something I added. You don't need to write this down. You're not going to be quizzed on this, but I think everyone should know. So radioactive isotopes. Many isotopes are unstable. And an unstable atom can emit particles or even change neutrons into protons to become more stable. This is known as radioactivity. Now, let me actually draw a quick sketch on the board as to why radioactivity actually occurs. Why are certain elements unstable?
You have like typing and you're not looking at it.
Yeah.
Well, it's not like he's gliding over.
He's
Okay, so let me draw a sample of a nucleus. Proton, neutron, proton, neutron, proton, neutron, proton, neutron. A couple extras. Like this. Has anyone ever wondered why this sticks together?
I know how it breaks off.
Right.
It sticks together.
Why would a nucleus stick together? These are all positive particles, right?
Because they're
Basically, it's something that is often referred to as nuclear glue, yes. I mean, if you think about it, if you took a bunch of positive particles and forced them to stick together, what would they want to do? Break apart, repel.
aren't they kept together by
Oh,
because the
I know.
electrons
I
are
think it's like nuclear
Nope.
glue.
I know. It's kind of like Chinese finger traps. The more you pull, the more it sucks that bad boy up. and-
Sorry, Quinn, it's not like that.
It's like quicksand.
Nope.
You fight it, that bad boy's gonna
Okay,
suck
Quinn.
right in.
It's a bad boy.
Here's why nuclei stick together. There is a second force of nature. What we think of in terms of plus and minus charges is called electromagnetic forces. That's your pluses and minuses. But there's a second force, which we call the strong nuclear force, which is incredibly strong, and yet it has a tiny range. The range of it is about 10 protons apart. Now, it's so strong that anything inside this range is just locked in place. It's basically like nuclear superglue. So even though these protons hate being together, and they're trying as hard as they can to push out, this strong nuclear force just doesn't let them. However, let's talk about what happens if we're going to add more and more protons to this as we drop down the periodic table. All of a sudden, what's the problem? What's going to happen?
You go outside the range.
Right, it's going to go outside the range. Now this dashed line here doesn't represent like a physical boundary. It's not like there's a shell. But eventually they're going to start going outside of this range.
And those ones are gonna break apart.
Well,
They zip
pretty
off.
much.
They zip off one another.
What happens here is this, each of these protons exerts their own strong nuclear force. So like this one in the middle has this one. If you're talking about this proton here, well, this one has a range of something like this. So this proton is locked into place with all of these. However, it's not locked into place with these, and it's actively trying to get away from them. This one here has its nuclear range of something like this. So this one is locked into place here, but it's not locked into place with these. What you end up with happening is these two forces on either side of a large nucleus pushing against another, and that's what eventually causes them to break apart. Basically, in groups of 1 or 2, depending on the type of radiation, it'll release protons and neutrons. By the way, we talked about Rutherford's experiment. We said the particle that he fired through that gold was an alpha particle, which existed as 2 protons stuck to 2 neutrons. This is one type of radiation. One way that this atom becomes more stable is it basically cuts off 2 protons and 2 neutrons, which leave, turning this into a new atom. You basically drop it down 2 numbers. Okay? So I just wanted to talk about why radiation actually occurs, or radioactivity. And let's talk about how we actually utilize it. So, could someone tell me what a half-life is?
It's like exponential decay. Well,
Good. What do you mean by that?
So if you have something and it'll go down. It's the amount of time it takes for it to be half as strong, but then it'll go like halfway from there, then halfway from there, and halfway from there.
Good. That was perfect, except it's not really half as strong. I mean, I guess...
No, half as much of it.
Exactly. So, radioactivity occurs at a constant rate. The time it takes for half of an isotope to decay is called the half-life. So if I have a sample of uranium-238, which naturally decays, after one half-life, half of that will have decayed. After the second half-life, half of the remaining would have decayed. Yep.
So some of the like really powerful stuff has like a really long half-life.
Yeah,
and that's
billions
why-
of years some.
That's why it's bad to have it. It's like it won't go away in our lifetime.
Yeah, I mean, that's one of the arguments against nuclear power. Most of the nuclear fuel that we use has half-lives of hundreds of thousands of years, and you need to wait about 7 or 8 half-lives in order for it to be safe enough on the surface. So what we do is we bury it underground and just kind of hope that nothing bad happens in the next million years or so. So, not to say I'm anti-nuclear with that argument, I'm just saying it's something we have to consider. So after one half-life, 50% of the original isotope remains. After 2 half-lives, what percent?
25.
25, good, it's not 0. It's half of the remaining sample. So after 2 half-lives, it's 25. After 3, it's 12.5. And this is basically how we use radioactivity to date things. Anyone ever heard of carbon dating? Yep.
Yeah.
So this is what we basically do. So carbon-14 is an unstable isotope of carbon with a half-life of 5,700 years. So that means that after 5,700 years, half of the C14 will have decayed into another element. Now, a lot of that happens through alpha radiation when it gives off an alpha particle, which is 2 protons and 2 neutrons. So basically, the carbon-14 turns into magnesium-12. Magnesium-12. Not magnesium. I'm looking at the wrong column. Beryllium. Beryllium-12. Beryllium-10. That's what it would be. It's losing 4 mass units. The example that we'll talk about is the ancient Egyptians used to mummify cats. Scientists are able to calculate how much C14 is present in a cat to find out its age. So, for example, let's say they find that only 25% of the expected C14 remains. How many half-lives must have passed? 2. So we know that each half-life is 5,700 years. 2 half-lives, 11,400 years. So that's how you age things.
Rough estimate of.
Yeah, it is a rough estimate. And carbon dating works up to about 50,000 years, because after about 50,000, you're dealing with like 8 or 9 half-lives, and it's kind of, the data is not really good enough. Fortunately, anytime we want to date anything that refers to like human civilization, it's within that 50,000 year range.
Is that
Well, humans existed for millions of years, but the first civilizations like Mesopotamia didn't really spring up until less than 50,000 years ago.
Is that like accurate? How accurate would that number be?
I don't know for sure. It's definitely, it gives it a range. It'll say like 11,400 years plus or minus a few hundred or a few thousand.
Okay.
That's still a lot.
All right, so this is the stuff that you do actually have to know, so let's get back to the notes. Atomic mass. Because most elements have different isotopes, each element has an average atomic mass. The number you see underneath, that's the average. The unit we use for calculating atomic mass is the atomic mass unit, or AMU. 1 AMU refers to the mass of a proton or a neutron. We don't count electrons in AMU. Why do you think we don't count them? Why do you think it's okay to disregard electrons?
Because electrons' weight is so small that it hardly counts for anything.
Right. They're about 1,800 to 2,000 times smaller, so it just doesn't even matter. Okay? The atomic mass of an element is a weighted average. So for example, I talked about two isotopes of carbon, carbon 12 and carbon 14. Well, you wouldn't say, okay, well the average is 13, so all carbon must be 13. It's a weighted average. The vast majority of carbon is carbon 12, a tiny, tiny bit of carbon is carbon 14. So that's why if we look up at the atomic mass, it says 12.011. That's because it would be 12, but it's kind of bumped up a tiny bit by the C14. So it's a weighted average. That's kind of the key point here. Now we can't actually calculate these. Calculating atomic mass from percent abundance. What this percent abundance means is, what percent of chlorine has this mass? So the first one, the relative mass is 34.9689 AMU, atomic mass units, and about 75.77% of chlorine has that mass. The other isotope is Cl37, and about 24% has this mass. If I were to ask you to find the average atomic mass, you would basically multiply this mass by the percentage, which you turn into a decimal. So how do I turn 75.77% into a decimal?
0.75.
Right, move the decimal point 2 places, so that becomes 0.7577. And you basically add them up. So why does everyone grab a calculator? You take your mass of the top one times 0.7577. You're going to add to that the mass of the bottom one times 0.2423. It should give you something that looks like a weighted average. Yep, you get your number from the top one, you add it to the number from the bottom one. Does this look right? Take a look at the periodic table for chlorine. Does that look right? Oh. When you're done, check your answer with the atomic mass of chlorine on the periodic table.
Read that. No, what's that say?
35.5.
What you want to do, Quinn, is find the mass of the first isotope, which is the
How can you see that?
multiply that by the percent abundance, which you
Very
turn into a
I have
percent.
bad vision.
So you're going to do 34.9689 times
Wait, it's like
0.7577. Find the answer, then you're going to add it to the same thing on the bottom, and it should come out to a weighted average.
You shouldn't have tried to close my
So
computer.
you should get something like, what you're doing here is finding the average mass of all the chlorine in the world. Because according to this, 3/4 of all chlorine exists as chlorine 35, 1/4 exists as chlorine 37, so the weighted average works out to about, Sean, what'd you get?
35.4527.
Right. So it should work out to about that, which you can check on the periodic table as well. Wait, go ahead.
So isotopes are basically just like one of something.
Yeah, you would say isotopes are different, like, versions of
Yeah.
atoms. So chlorine 35 and chlorine 37 are two isotopes.
Yeah, see, but they're both chlorine atoms, but you got this isotope, you got this.
Right. Sean? Or Brad?
Can you explain it, AMU?
What?
Can you explain what the
AMU?
AMU is?
Yes. AMU stands for Atomic Mass Unit. It's basically the unit that we created for this purpose. Okay? So here's another example, but we don't need to run through this. You would do the same basic process. All right, just want to quickly review mass number versus atomic mass.
It looks like
I
AMU.
think it's a.
Shh, Brad. Quinn, come on. The mass number, which is protons plus neutrons, is unique for every atom. It's a sum of protons and neutrons. You wouldn't say, what's the mass number of carbon? Because that doesn't make sense. Carbon has different isotopes. You would say, what's the mass number of a particular carbon atom that has X number of neutrons? Different atoms of the same element have different mass numbers. They're called isotopes. It's really nothing new. If you've got the notes before, you don't really need this. And mass number has no unit. It's just the number of protons plus the number of neutrons. So there's really no unit. And the difference here is that atomic mass is the weighted average of the mass of all the isotopes. So for that reason, you wouldn't say what's the atomic mass of an atom with 6 protons and 5 neutrons. You would say what's the mass number. The context for atomic mass is something like what's the atomic mass of calcium? What's the atomic mass of phosphorus? So you're talking about a different element for that. Questions about these? Yep. Atomic mass is the weighted average of all the isotopes. Now, the long answer for that is you look at that chart we just looked at and you add them all up. The short answer, look at the periodic table. It's a number underneath. So, for example, for rubidium, it's 85.4678. That means that some rubidium atoms have a mass of less than that, some have a mass of more than that. Okay, what do we have here? 45? Okay, we're going to revisit the Bohr model and talk a little bit about photochemistry. Now, before we get to that, what does the term photo mean? The prefix photo. What do you think photo comes from?
Before.
Light. Photo comes from light. So we're going to study the chemistry of light. Now, what I have on the next slide is kind of background knowledge. You don't really need to take down everything on this slide, but just understand it. So this is your Bohr model. The way Bohr came up with this model, he didn't just think of it. He came up with it based on research by Max Planck and Albert Einstein, 2 German scientists. Yes, definitely heard of Einstein before.
Not Planck.
Planck proposed that energy was not continuous like a beam. So if we think of like an energy wave, we sometimes think of it as being continuous, like the sun is just continuously shining on us. But on the most tiniest particle level, energy is not continuous. It's in discrete bundles or like packages almost. Think of it as like little units of energy. So the sun is not like shining a continuous beam on us. It's basically like a machine gun firing little units of energy at us. That's sort of the first step of this information here. Okay? This term means energy was thought of as quantized. Quantized, think of quantity as in like numbers, or there's like pieces of it. It's not continuous. Einstein continued this theory and proposed that light itself was quantized. So that's like sunlight. It's not a continuous beam. It's like basically firing little particles of energy at us. He called one bundle of energy a photon. There's your photo, meaning light. This research led to Bohr's model. So Bohr concluded that electrons, when struck with light, they gain energy and jump up an energy level away from the nucleus. So this electron in here absorbs 1 unit of energy, or 1 photon in the case of sunlight, and it basically jumps up to level 2. So it starts with low energy, it jumps up a level. Because light energy was quantized, meaning because light doesn't exist as this continuous sort of beam, it's because it has certain units, electrons absorbed a photon and jumped up to a higher level. This is why you can't ever exist between 1 and 2. The energy of 1 photon takes this electron from exactly where it is here to exactly where this one is here. You can't absorb half a photon or 2/3 of a photon or 1.5 photons. It has to absorb exactly 1 photon, which forces the electron to go to exactly this orbit, and that is why electrons exist on those preset axes, as we said. The 2 terms we use for electrons in this context are excited versus ground state. They start as ground state with their low energy. When they're hit with a photon, they become excited, and that's when they jump up. And this is why distances from the nucleus are fixed and not random. It's because it has to absorb a certain set amount of energy, and by absorbing exactly that amount of energy, it jumps up to exactly that level around the nucleus. Questions about this? All right.
When there's the electrons are shared atoms.
When they're shared. It's a good question. Basically, the orbitals start to overlap when they're shared, so they still jump up away from both nuclei.
So we know exactly what to do.
Well, they don't know, they're forced.
Well, even if there's two nucleons.
Yeah, and it's not like they make the decision. Basically, if you have two nuclei, they can't move really towards either of them. So they have to move away from them. So they can basically go to the left or to the right. And you're given a certain amount of energy, which forces them to go a certain exact distance away.
Okay.
Yep. Last comment here is just reiterating that this is the lowest energy level.
But we proved this is wrong.
All right, Brad or Quinn, which one of you guys wants to move? Because it's been constant.
Brad,
I'll go.
definitely.
Thanks.
I just have a question.
Yep.
Didn't we prove that wrong since it's not levels, it's a C? So then,
Yes. However, the idea behind it is still true. Bohr thought it was these perfect circles. We've proven that wrong. It's not these perfect circles anymore. But they still do jump up levels.
so it's more like they can be anywhere on like a
Right, and in fact,
You're
in-
always trying to get to 8 or 1.
No, that's a little different. In fact, that question and your question will be answered in next week when we talk about the configuration of electrons and where they actually go. What we're going to do in the next 15 minutes, talk about atomic spectra. Spectra is the plural of spectrum. When you heat an element, there are countless electrons changing their energy levels or distances from the nucleus. They're jumping up, they're jumping down.
Wait, which part do we have to write? All of us?
You should understand this stuff. If you want to write it down, I would do so. I mean, these slides will be up on Endline. As the electrons lose energy, they release energy as photons, which give off light. That's kind of the key here. Energy is given off by electrons as they lose energy and have to back down towards the lower levels. And that photon is what gives off light. Like when I'm looking at something, what I'm seeing is the electrons, like in that cabinet, jumping back down, and that's emitting light, which my eyes perceive as blue. That American flag, basically the photons from these light sources hit the electrons in that flag, causing them to jump up energy levels, which they exist for a split second. They jump back down. By jumping back down, they emit a wavelength of light, which my eye perceives as red or white or blue. That's how we see color.
Wait, I have a question. So the reason like if there's no light and we see something in the dark, because there's nothing jumping up for us to see, or it's jumping up less, I guess.
Right. There's not enough light to excite the electrons enough for us to perceive it.
Okay.
Each element has its own atomic spectrum. So when you see an element glowing in a certain color, it's unique to that element. These are some examples of atomic spectra. And here I have 5 of them. What we're going to do is work with these spectroscopes. You may have seen these before, physical science, possibly.
Yeah, I have it.
Okay? Now, what we're going to do first is get our eyes used to how to work these. So I need everyone to quiet down, please. Basically, you have a vertical slot. You want to hold this like this. And you want the vertical slot to be on the right side. If it's on the left, just flip it upside down. You're going to point that vertical slot at your source of light. So like I'll use the board, you could also use these lights. And you want the light to shine through there. But then you don't want to look at the light through the slot. You want to turn your eyes to look at the side. So aim the slot at the light, but then look to the side. And you should see distinct little lines. Now when you look at white light here, you're actually going to see pretty much everything. And that's because white light, you may have heard, is like a combination of all colors. So like when I look at these fluorescent lights, I basically see every color. What was that?
Does it hurt your eyes?
No. But then what we're going to do is isolate different elements using this spectrum tube, and you'll see that you don't see every light, you only see certain ones. So let me get everyone to come up. In fact, 1 person per table, please. Grab 1 for every person. For now, I want you guys to practice working with these by looking at the board or the lights. try to just see the different colors. It's basically like a prism, which breaks the light into its different colors.
What is this thing? Am I looking the wrong way? Looking into it.
I see.
I suggest you have the vertical slot on the right side. Aim the slot at the light, but then don't look at the light.
yeah, it's a
Look
rainbow,
to the side.
It's a rainbow.
It's on the left.
Quinn, can I look at you?
Pride.
Whoa!
This is sick.
I don't see
It's like
it. What are you playing? I like to do. I like
Oh, I
looking
can
at
see
you.
It basically splits the light up. Make sure it works.
It does.
Yeah.
Whoa,
What it's
right.
doing is-
So
Have you guys ever seen like an image of light passing through a glass
It does
prism?
it on Pink Floyd
shirt. Like Pink Floyd.
Yes, yeah. Oh, well, that's because his shirt is bouncing light off your shirt.
Oh,
wanna see what-
cool.
When is
You don't have to
it?
try it. Whoa!
Oh, now I see nothing.
The board should still work, guys, if you want to check the board.
Whoa, Bohr works. It's even cooler.
Yeah, because now it's distinct white light. That one-
I don't see it.
That one doesn't work.
I just see blue and green. Sit down now.
I see a rainbow. You see blue and green?
Yeah, there we go.
I only
Alright.
see blue and green.
So guys, what you've been looking at is basically the full spectrum of colors. What I'm going to do now is demonstrate certain individual elements using this spectrum tube. Now, you have to be probably within 15 feet for it to work. So I'd say we kind of work in two waves, like one wave first and then the other wave. So once you sort of gather in a semicircle,
I see.
But what happens if we look into it?
So, the light of my life.
it's not that bright. Alright, the first one I'm going to demonstrate is hydrogen gas. I have hydrogen in this tube. And by putting it in this machine, it's basically going to heat up the hydrogen. And it's going to give energy to the electrons. The electrons are going to become excited. They're going to jump up. They're going to lose that energy. They're going to jump down. And they're going to give photons, which you see as light. So, when you look through this, you should notice not a continuous spectrum. You should see like 4 or 3 distinct lines. See if you can identify them.
Oh, red.
Oh my god.
And if you can't see, you might need to come
Might be
closer.
green, yeah.
It's
Turquoise.
like a. Oh.
This is teal,
What the land you block?
Oh, I see red.
teal, red, and violet.
Yeah.
It's a cool sound effect, right?
Yeah, I'm seeing 3 lines on mine. I saw 4 on
Teal, red, and
earlier
violet.
today.
I have
I
4.
see 3.
Teal, scarlet, and violet.
Yeah, that's what I see.
Now, if you guys from here, if you can look at my computer over there, that shows what the actual spectrum is. Not through the thing, put it down. But like through scientific discoveries, we've tracked that hydrogen should have those distinct marks. So what that tells you is this might not be pure hydrogen. More realistically, these aren't, the best spectroscopes in the world. But you should see, so Brad, how many lines are in that top bar?
There's 1 red, 1 green, 1 blue, and 2 purples.
Yeah, so you should see 5. These don't really see the purples that well, so you probably clearly see 3. So that's hydrogen. Now, I don't want to heat these up too long because they do get very, very hot to the touch. I'm going to do a different element now. Guys, quiet down. This one contains helium. Now, how many electrons does a hydrogen atom have?
2.
Hydrogen.
Oh, 1.
1. Helium has 2. So there are twice as many electrons that are jumping up, jumping down, jumping up, jumping down. So do you expect more or less lines? Probably going to see more lines. So let's check this one
Is
out.
this helium?
Yes.
It's so white.
Alright, so this one is helium.
Doesn't that mean it will heat up more and will hurt more?
Can I just look at it?
I see red, orange,
Brett, get out of my view.
green lines.
Oh wow.
Green
Look at that
the teal
orange
lines.
color.
Whatever they are, they're green to me.
That orange color.
Teal is for
Do you see this color? Oh,
I gotta get
very cool.
What?
Very nice.
Yeah, for my stool.
I have 7 parts.
We did something like this in a year last week.
I just wish we were in physics so we could
We
read
made
physics.
Yeah.
I have 6.
I have 7.
Very interesting.
I know, I have
We'll
7.
get pretty close to that.
Ian, 2 purple.
Well, Ian, you heard
We're not going to do this MC squared, but we'll deal with C. We'll deal with E.
Oh, Ian.
All right. So that is
What about M
helium.
squared?
Could someone go near my computer? Can you just read me like what types of lines you see for neon? What do we see for neon, guys? Guys,
2 yellow, and the rest are like reddish, orange.
all right. So guys, if you can see from here, neon is the third one down. So I have neon in this too. You should see mostly reds, oranges, and yellows. Let's test that out.
I like this.
So that's neon.
Whoa, there's a lot of Roy, as in red, orange, yellow.
Not so much Biv, right?
Not so much big.
I have way too many lines.
I see some green. Oh,
I
Yep,
see some
there are
fuchsia.
some greens.
I see some
Oh, I
fuchsia.
see some.
Hold on, I can't even count
This is
them.
pretty.
Now, not only do you see a lot of lines though, and that's the key, because this has like 70 times more electrons than the other ones. Well, not 70. What is it? Like 40? This has a lot more electrons, so you see a lot more lines. Yeah, my gosh.
Oh, you can't see from that side?
Correct.
Oh, yeah.
Why not?
The prism only works one way.
Oh, that's
This is neon, so the term neon light refers to this. Now, neon lights do come in different colors, but pure neon lights are only this color.
wow.
If you see neon lights that are like purple, well, it's probably something more like krypton or argon gas or xenon gas.
Oh, I
Why
got a
don't-
product
What happens if you
on
break
neon
that?
instead
Like,
of
I mean, like,
green.
what would come out?
Gas.
Yeah. Let's try it.
We got a second.
All right, we'll do one more.
Like, right.
I'm gonna look at the
Thank you. Actually, let off.
Okay, I'm not yet.
Brad.
What are you doing?
Now you know.
Please consider.
This one is mercury. So you look at mercury.
Oh, that's gonna be bluish. Hey.
How'd you know, Ian? You did this at home?
I know.
It's going to die.
What colors do we see in here?
Red, orange, green, but more purple.
I
I think
see a
all
lot
of them
of
except yellow.
Yeah, more kind of bibs than
Wait,
roids.
I have a yellow.
I have a red.
You might have one yellow, one red.
Don't lie.
But
Don't
for the
lie.
most part, you're
What is this?
seeing this is mercury.
I see orange and green.
What?
I have a deeper. I have a fourth green.
Really face strobe light.
Yeah, this one's not as bright as the others.
Strobe light.
Oh, Ian.
Yeah.
Oh.
Oh, that doesn't
Yeah.
do this strobe light.
All right. So that brings us to the. We'll wrap this up. I can't let this go too long to get very hot. Let me pause this.